This is a GCSE chemistry tutorial looking at the electrolysis of aluminium. This fits into topic 4. So where do we find aluminium? Well, aluminium, like most metals, is found as an ore in the ground. Aluminium's ore is called bauxite. Bauxite is a red mineral made of both aluminium oxide and iron oxide, and it's mined all over the world, but in particular in both Russia and Jamaica. In order to manufacture aluminium, we first need to purify the bauxite. We looked at purification in the redox tutorial. To do this, bauxite is heated with sodium hydroxide, which dissolves the alumina but not the other materials. The residue is then filtered off and disposed of. The filtrate can then be acidified and heated to produce pure alumina, which is aluminium oxide powder. So we've been able to purify our bauxite, which is a mixture of aluminium and iron oxides, into pure aluminium oxide. Unfortunately, aluminium is more reactive than carbon. This means that we can't carry out reduction via the use of carbon in order to extract our aluminium from our aluminium oxide. This means we cannot use a blast furnace like we would for iron. This means we have to use the more expensive process of electrolysis, as we looked at in the electrolysis and half equations video. Because aluminium is such a valuable metal in the modern world, it has a specific set of conditions. Its electrolysis cell looks like this. We're going to break it down into each part. The electrolysis cell looks like this. We have the cathode, which surrounds the entirety of the solution, and the anode is found at the top. Like any electrolysis, we provide a direct current in order to separate the ions. Our aluminium oxide is Al2O3, and so we have O2- and Al3+ ions. The anode, the positive electrode, will attract the negative oxide 2- ions, and this is what we will look at first. In order to carry out this electrolysis, we need a very high temperature. This very high temperature is needed because we need to melt our aluminium oxide in order to have ions in the liquid. At the anode, the oxide 2- ions are attracted to the positive anode. At the anode, the oxide ions lose 2 electrons each in order to become oxygen gas, which is O2. This means that our balanced half equation is 2O2- goes to O2 plus 4E-. Because they are losing electrons, this means that they are being oxidized. The anode that we use is a graphite anode. We use a graphite anode because it is inert. However, because graphite is made of carbon and this process takes place at a very high temperature, this means that the oxygen that we are producing reacts with the carbon anode, producing carbon dioxide. This means that the carbon graphite anodes need to be replaced regularly because they are being burnt away during combustion. So what happens at the cathode? Well, the cathode, the negative electrode, is where the positive Al3+ cations get attracted to. As the Al3+ cations get attracted, they gain 3 electrons in order to become aluminium. Because of the very high temperature, this is liquid aluminium that is made. Because they are gaining electrons, this is an example of reduction. So in summary, for the electrodes, at the negative cathode, we have positive aluminium ions going towards the cathode, where they gain electrons and become aluminium atoms. At the positive anode, it is the negative oxide ions that move. There they lose electrons and become oxygen gas molecules. These oxygen gas molecules then react with the carbon in the graphite electrodes to produce carbon dioxide gas. We then need to balance the overall equation using the two half equations. The two half equations we have, Al3 plus in the liquid form, plus 3 electrons goes to aluminium as a liquid. 2 oxide ions, 2 O2 minus in the liquid phase, goes to O2 as a gas, plus 4 E minus. In order to balance this, we need to find the lowest common factor that both 3 and 4 go into. This is 12. In order to balance this, we need to make both of them 12 electrons. For the aluminium, this means timesing it by 4, giving us the new half equation. 4Al3 plus 12 electrons produces 4 aluminiums. And for our second half equation, we need to times this by 3, giving us the new half equation. 6O2 minus goes to 3O2 plus 12 electrons. We can then write a full balanced equation as we can cancel out the electrons, giving us the final equation. 4Al3 plus 6O2 minus goes to 4Al plus 3O2 minus. We can then combine this with our original formula of Al2O3 to give us the overall equation. With our overall balanced equation for the electrolysis of aluminium from aluminium oxide being 2Al2O3 goes to 4Al plus 3O2. So why are we particularly interested in aluminium? Well, aluminium is one of the most used metals in the modern world. We can use it for power cables, we can use it for aeroplanes, we can use it for cooking foil, and we can even use it for space blankets and window frames. This is because it is very low density, it conducts heat and electricity, it is also very unreactive. This is despite aluminium being quite high up in the reactivity series. This is because when aluminium is cut, it reacts very quickly with the oxygen in the air to create a thin layer of aluminium oxide which surrounds it. Aluminium oxide is highly unreactive. It is very malleable and easy to work with, while also being very strong. We will look at aluminium more in the Earth's resources topic, where we look at the recycling and life cycle assessment of aluminium products. This means that aluminium is a topic that the exam boards can test your knowledge across various different aspects of the course.